So section 1.3 is about simplifying radical expressions. I want to kind of do ones that work out nicely and ones that don't work out so nice, and we'll go from there. Remember what and then remember we're doing 15 to 63, and that was typed wrong. It should be 5 to 63, and I'll change that in a minute. But do we want to just do the odds? Yeah, we'll do odds, 5 to 60. Okay, so let's start with number 5. If you recall, what a square root is saying is what number squared gives you 256. So if we think about 256 is 16 squared. So the square root of 16 squared is 16. So you're looking for the number squared that gives you that. Okay? And so I want to talk about one like number 7. For a problem like number 7, it is the square root of that thing, that answer. So you want to completely get the answer inside of number 7 before you take the square root. So that's 4 times 25, which is 100, which the square root of 100 is 10. Okay. Now, not all square roots work out perfectly, so let's just for a minute look at how we deal with one like number 11. For number 11, the square root of 98. Since 98 is not a perfect square, there's no number that gives me 98 if I square it. So instead, what we can look for is the largest perfect square that lives in 98. So, if you think about all the perfect squares below, from 98 and below, the highest one is 81, that's 9 squared. And then, if you keep working your way backwards, the only number that goes into 98, or the largest perfect square, is 49. That's 2 times 49. Now, the reason we do that is so that we can remove the largest perfect square that is contained in the number 98. 49 is 7 squared. So you can kind of think about this as 2 separate things, the square root of 2 times the square root of 49. So I can deal with the square root of 49, that's 7. I can't deal with the square root of 2, so you just leave it contained inside the square root. So that happens sometimes as well. Now, in number 7, the addition was inside the square root, so we had to do that addition first. For 15, the square root is on the outsides of the addition, so you do each individual square root and then add the 2 answers together. Now, I would like to do one like 19 with you. For problem 19, the only way to add 2 square roots, so let me kind of show you. If you have 2 square root of 3 plus 4 square root of 3, that's 6 square root of 3. So the rule is I can only add radicals if they are perfect matches. And you add them almost like if they were 2x plus 4x is 6x. 2 radical 3's and 4 radical 3's is a total of 6 radical 3's. So that's kind of how you do that. So if you look at 19, the way that it sits, I can't do a thing. I can't do anything with those radicals. Bless you. They don't match. Square root of 6 and square root of 24 are unlike terms. It's like an x and a y. But since 24 is 4 times 6 and can be reduced to 2 times square root of 6, I can get it to be a square root of 6. Now, what the 2 does is it multiplies by whatever is already currently there. So this technically would be 14 radical 6's minus 12, because 2 times 6 is 12 radical 6's, for a total of just 14 minus 12, or 2 radical 6's. So in order to add radicals, they must be perfect matches inside the radical, and then you add or subtract the front coefficient. Now let's talk about 23. 23, the first thing I kind of look for when I multiply radicals are, is there any perfect squares? Well, 42 is 6 times 7, nothing's a perfect square. 30 is 6 times 5, nothing's a perfect square. But if we think about this, this can be the square root of 42 times 30. And maybe they have something that's in common. Well, 42 is 6 times 7. 30 is 6 times 5. Since they both have a 6, which when combined makes a 36, or 6 squared, that part can come out. So that can bring a 6 out in front. Now I'm still left with a 7 and a 5 inside. So you can write 7 times 5 inside and then multiply it, or you can just multiply it. 7 times 5 is 35. So it's 6 radical 35. So sometimes multiplying ahead of time makes things worse, because then you just have to pull it apart. If it's not a good radical, pull it apart first. Try to find matches that you can square root, and then leave the rest. So there is 23 for you. I would like to, we'll do 29 together, but first let's do a fraction. Now, for 25, both top and bottom are perfect squares. You square root the top, square root the bottom, and reduce it. But let's look at 27 because it's not quite like that. Okay. 360 over 361, they're not perfect squares. I think about 360 as 36 times 10. Well, why 36? Well, 36 is a perfect square. And I like that I can do that. Let's talk about the number 361. I'm just trying to see if it has anything good in it. I don't think it does. A little trick you can do is if you add up the digits, 3 plus 6 is 9, plus 1 is 10. If the digits add up to a number that's divisible by 3, the whole thing is divisible by 3, so it's not divisible by 3. It's not even, so it's not divisible by 2. Oh, does anything go into 361? I think it might be prime. But let me check for you real quick. So usually if you go online and search for the list of prime numbers, you can usually find if 361 is on there. I'm checking. Is 361 prime? Okay, so it's not prime. So what goes into it? Let's see if it's divisible by 17. Nope. Oh, it might be 19. Let's see. 361 divided by 19. Oh, it is. Okay, I wasn't even thinking 19. That is 19, did I say? I was trying 17, but I wasn't trying 19. Okay, so what do we have? Well, on top, the only perfect square we have is 36. On the bottom, that's 19 times 19, or 19 squared. So we do have some things that can come out of there. 6 can come out on top. That leaves a 10 on the bottom. Leaves a 10 up there. 19 squared is in the bottom, so that's a 19. And then you always want to check with fractions, are the pieces that are on the outside reducible? 6 over 19 isn't reducible, so you're good. I want to talk about now, sorry that took me so long. Let's talk about 29. Back in Algebra 2, you probably learned something about something called a conjugate. If you have two pieces like this in a denominator, you can't leave it there. So you're going to use something called a conjugate. And we've talked a little bit about conjugates. So what we're going to do is we're going to do a little cheat. We're going to multiply both the top and the bottom by 1 plus the square root of 17. Okay. So on top, I'm going to let you try this, but on top, you're going to distribute the 8. On the bottom, when you go and distribute, you're going to get some nice things happen. So give that a shot yourself, and then if you have questions, just let me know. So multiply top and bottom by the conjugate for 29. Let's look at 31. 31 has that little cube there. You may recall from Algebra 2 that refers to a cube root. A cube root, we are looking for something cubed that contains that number. So like 2 cubed is 8, so 8's a good number under a cube root. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. So those are some to get your brain thinking of cubes. So currently, like any radical, we can only add them if they're perfect matches. Those are not perfect, those don't match. But what do we know about the number 128? Well, 128 is 64 times 2. Now, one hint that I'm looking for a multiple of 2 is the fact this one has a 2 stuck inside. So why not find maybe the 2 that's over there? Because 64 is on my list. So it's a perfect cube. It's 4 cubed. So that brings a 4 out in front, leaves a 2 inside. So I have the cubed root, 4 cubed root of 2's plus 3 cubed root of 2's is 7 cubed root of 2's. So you have to get the radicals to match, whether they're square roots or cube roots, before you're allowed to add them. And then you add them by adding the front coefficients or subtracting. 33, I think would be okay. Now, starting with 35, those ones contain some x's. Now, our rules of powers that we talked about a week ago or so are going to come into play. What a square root does is it divides the power in 2. What a cube root does is it divides the power in 3. So let's just start out with this first one here. You kind of separate it into 2 pieces. The square root of 400, what number squared gives you 400? 20. And then our power gets cut in half because the square root is what number squared would be x to the 4th. So just cut the power in half. So that's x squared. So that's as easy as it is, okay? So for 37, we have one piece that is a perfect square, 49. But p is not a perfect square because it isn't an even power that I can cut by 2. I can't cut that in half. Now, it's not a bad idea to write it as 7p to the 1/2. That's perfectly legitimate answer. That's the correct answer. But I think they want you to keep it as radical. So that means I can deal with the 7, but the p is still stuck in the square root. So both of these answers I'll accept they are correct. It's just a matter of what are you looking for. And that's 37. Let's go down the list here. Okay, let's do 41. So what I notice is the radicals don't match, so I currently can't add them. So then I look for some way, can I reduce that radical? Can I make it prettier? Well, b squared is a perfect square. Its power is divisible by 2. So let's divide that power by 2 and bring it out in front. So we have 3b square root of a minus b squared of a. Now, look what has to match. The b and the square root of a have to be perfect matches, which they are. Now we can subtract the front coefficients. 3 minus 1 is 2. So we have 2 of those b square root of a's. So you can only add or subtract them if they're exact perfect matches. There's 41, so I think you could probably try 44. Let's do 43. So I always try to kind of reduce a fraction if possible. This x cubed and x can reduce because remember the rules of powers we discussed when we worked on 1.2. If the bases are like we're dividing, we subtract the exponents. So our exponents are 3 and 1. 3 minus 1 is 2. And so that is really the square root of 225x squared over 49. Now 225 is divisible by 15. It's 15 squared. 49 is 7 squared. There's nothing I can reduce there. So now let's just take the square root. Take the square root of the top over the square root of the bottom. And then you can always look again to see, can I reduce anymore? If I can't reduce anymore, it is what it is. There you go. So there's 43. Let's jump to, let's go to 50. We'll do 51 and 53, maybe 57. Okay, let's go to 50. There's no way to add those together. Not only do the w's have to match, well, they do, that's good, but the square roots have to match before we can add anything. So variables have to match and square roots, and they don't. But there's something hiding in a 32. That's 16 times 2. $50 is 25 times 2. Now, why is all that helpful? Well, the reason that helps me is the perfect square on both of them will come out, and both of them will leave a 2 back behind. So the square root of 16 is a 4. Put it out here. Then we still have that w to the 3/2 and then a square root of 2. Square root of 25 is 5, but let's put that in the front. Now, you can combine them only because the w to the 3/2 match and the square roots match. So the variables have to match and the square roots, or you cannot combine them. You can combine them by adding or subtracting the front coefficients. 4 minus 5 is negative 1. So we have negative 1 of those w 3/2 square root of 2's. Now you don't have to put a 1 physically there. You can just put the negative symbol. Doesn't matter to me one way or the other. You decide. So there is 51 for you. Let's look at 53. Earlier we had one that we had to use a conjugate. If you have any addition or subtraction in the bottom that can't be combined, you're going to want to use a conjugate. So surrounded by parentheses, multiplied by 2 minus 2 square root of 3 on top and bottom. Now there's a few different, this one is a little complicated, so let's do this one together. Okay, so if we distribute this, we get 2 square root of 12x minus 2 square root of 36x. Okay, that's just distributing the top. If we distribute in the bottom, we end up getting 4 minus 4 radical 3 plus 4 radical 3 because of that difference of squares. That's why we use a conjugate. And then we get a minus 4 times the square root of 9, which is 3. Okay, so we get that. And you can test that out if you take the distribution a little slower. So what do we get on top? Well, unfortunately, there are some things that can reduce, but not much. That 12 is 4 times 3. So 2 times the square root of 4 times 3x. It leaves a 3x behind, the 4 comes out. So that's 4 radical 3x. Now this one's a little clear. The 36 square rooted is just a 6. It comes out, multiplies by the 2 that's there. And on the bottom, 4 times 3 is 4 minus 12, which is negative 9. Now, unfortunately, we can't do much. This 4 and this 12 are not common factors of 9. There's nothing in common. We never leave a negative in the bottom, so we are going to divide both of these by negative 1. That's the only thing you really should do at this point. So the final answer would be negative 4 radical 3x plus 12 radical x over 9. You can't reduce the 12 and the 9 because the 4 doesn't have something in common. So unfortunately, that one's that's disgusting, but hopefully that helps you think about it a little bit. Let's keep going here. Let's do 57. You have to do up to 63, so we'll do maybe a few more together. Let's do 57. I try to reduce them a little bit. 81 is 9 squared. I just learned 361 is 19 squared. So 9 and 19 aren't common. You can't do anything. So that's going to be 9 over 19. Okay. Now what's still in the square root? Well, the m on top and the m squared would just leave me an m down in the bottom. So I'm going to write it as a 1 over m. So technically, we have a square root of 1 on top, which is just a 1. And we have this extra square root of m on the bottom. Well, if you end up with an m or a square root in the bottom that has like a 1 plus a square root or a 1 minus a square root, we use the conjugate. For one like this that just leaves that m in the bottom, we don't use the conjugate. We just use an extra square root. So we just multiply top and bottom by whatever the square root happens to be. And so we get 9 square root of m over 19. And you can't really do anything. So that's kind of a weird one. We're just practicing doing some radicals. So I think you'll be okay reducing 59. Let's talk about 61 because it's a 4th root. We haven't come across any 4th root yet. Let's think about 4 things to a power of 4. 2 to the 4th. It's 2 times 2 times 2 times 2, or 16. 3 to the 4th is 3 times 3 times 3 times 3, or 81. 4 to the 4th, I think it's 256, but let me do it real quick here. Yep, 256. Let's do one more. 5 to the 4th. I think it's 625. Yep. Okay. Keep those in mind if you're dealing with 4th powers. So does anything on that list go into 162? Well, yes, 81 does. So that's a good number. So that's 81 times 2. Now let's look at our x's for just a minute. We have 6 in the top, 4 in the bottom. So we technically, when reduced, the bases are alike and we're dividing, subtract the exponents. 6 minus 4 is 2. That leaves an extra 2 x's in the top. Now let's deal with the 16. 16's on our list, so just leave it 16. Okay. So if it's anything on that list, or if the power is divisible by 4, we can take it out. So I can take out the 81, it's on the list. I can take out a 16, it's on the list. So the 4th root of 81 is 3. The 4th root of 16 is 2. What's stuck? Well, I still have inside the radical the 2 in the x squared that I've done nothing with. So you leave it. That's as far as you can go. So take out as much as you can. What's nice about cubes, fourths, and even square roots, it's a very limited list that you get to deal with. So it's not a bad idea to write this little list on the side of your paper. What are some of the squares? What are some of the cubes? What are some of the fourths? And it would help you to go through it. Okay? Let's do 63, and then you'll have time to continue this on your own. Let's do 63. Now these are cubes. You might wonder, what do you do because there's a negative in there? Well, if it's a square root of a negative, that's an I. It's that imaginary component. Here, a cubed root of a negative is just negative, because negative times negative, 3 negatives make a negative. So the first thing I could do here to make it look a little nicer is I could take out the negative and make that a positive, so I don't have to worry about it. Okay, now let's think of our cube list. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. I think that's as far as we need for these numbers. So 128 is not on our list, but 128 is divisible by 64. That's 64 times 2. So let's make that 64 times 2. Remember, cube roots, we only care about numbers on this list. 16 isn't on our list, but 8 goes into it. So let's write that as 8 times 2. Okay. Now, a cube root takes a power that's on a z, like this case, and divides it by 3. 3 divided by 3 is 1. So both of those are perfect cubes. Divide that by 3. You're going to get the z's are going to be 1. The cubed root of 64 is 4. The cubed root of z is cubed is z. The only thing left in this one is a 2. And if we do the next one, the cubed root of 8 is 3. That comes out. The cubed root of z cubed is z. That comes out. The only thing left I haven't done anything with is the 2. So it stays back. Now, how do we know we can deal with this? Well, if the variable and the radical match, both of our variables and radicals match, we can add the front numbers. 4 of them plus 3 of them is a total of 7 of those z radical 2's. Do I know what a z radical 2 is? I don't know. I have 7 of them. Okay. So that gets you started, hopefully. So you're working on the odds, 5 to 63. Okay.